Right now, at this very moment, the Taiwan Strait is one of the most dangerous stretches of water on Earth for engineers. 130 kilometers of open ocean, average depth 60 meters, violent monsoon currents ripping through at 4 knots, and a seabed laced with active fault lines sitting squarely on the Pacific Ring of Fire. No one has ever built a tunnel through anything like this. The Channel Tunnel between England and France is considered one of humanity's greatest engineering achievements. And it crossed a calm, shallow, geologically stable seabed just 50 kilometers wide. The Taiwan Strait is nearly 3 times longer, 4 times deeper in its worst sections, and runs through earthquake-prone rock that shifts without warning. And yet, Chinese engineers have drawn up the blueprints, allocated preliminary budgets exceeding $100 billion, and identified the route. Pingtan Island on the Chinese mainland to Hsinchu on the western coast of Taiwan. A twin-bore, high-speed rail tunnel that would carry passengers under the ocean floor at over 400 kilometers per hour, connecting 2 economies separated not just by politics, but by the raw, violent physics of the Pacific Ocean. This is not a question of whether it can be built. This is a breakdown of exactly how they would build it, meter by meter, from the first cut of seabed rock to the first train pulling into Taipei.
130 kilometers of ocean, 3 active fault zones, earthquakes, typhoons, and a seabed nobody fully understands.
Before a single machine touches the ocean floor, the geology has to be mapped with a precision that borders on obsessive. Survey ships equipped with multi-beam sonar arrays and sub-bottom profilers spend months crisscrossing the strait, firing acoustic pulses into the seabed and reading the echoes that bounce back from buried rock layers. What they find determines everything. The Taiwan Strait seabed is not uniform. The western approach from Pingtan sits on relatively stable Mesozoic granite, but as you move east toward Taiwan, the geology transitions through layers of sedimentary sandstone, weathered basalt, and loose quaternary deposits. Soft, wet, unstable ground that collapses under pressure. And then there are the fault zones. At least 3 major tectonic fracture systems cross the proposed tunnel alignment, each one capable of producing earthquakes above magnitude 6. Every fracture must be located, measured, and mapped in 3 dimensions before the route can be finalized, because the tunnel cannot simply avoid them. At 130 kilometers, you go through them. You engineer around the movement. The construction begins on land, at Pingtan Island, where a launch site the size of a small city takes shape over 2 years. 40 hectares of coastal land are leveled and reinforced with deep piled foundations driven into bedrock. Concrete batching plants capable of producing 12,000 cubic meters of high-performance marine-grade concrete per day are erected. Rebar fabrication yards process steel reinforcement cages for the tunnel segments, each cage weighing over 8 tons. A purpose-built port facility with deep-water berths allows the largest construction barges and segment transport vessels to dock and load. On the Taiwan side, a mirror facility rises at Hsinchu, cut into the hillside above the coast, its tunnel portal already visible as a gaping rectangular void, reinforced with rock bolts and layers of shotcrete sprayed onto the exposed cliff face. These 2 sites will operate simultaneously, around the clock, for the next 15 years. Everything that goes into the tunnel, every bolt, every segment, every kilowatt of power, flows through these 2 points.
What you are looking at behind me is a 65,000-ton concrete section about to be sunk to the ocean floor.
The tunnel itself is not one continuous tube. It is built in 2 fundamentally different ways depending on what the seabed allows. In the shallower approaches near both coastlines, where water depth is under 30 meters, the immersed tube method is used. Massive prefabricated concrete tunnel sections, each one 180 meters long, 25 meters wide, and weighing 65,000 tons, are cast in dry docks near the launch sites. Each section is a sealed, watertight concrete box with internal dividers, creating 2 separate rail bores and a central service gallery. Once cured and fitted with temporary steel bulkheads at each end, the sections are floated out of the dry dock like enormous concrete ships. Tugboats, 6 of them per section, GPS-guided to centimeter accuracy, tow the floating section out to its installation point in the strait. Below the surface, a fleet of dredgers has already carved a precise trench into the seabed, 10 meters deep and 20 meters wide, with a gravel foundation bed leveled by underwater grading machines to a tolerance of plus or minus 30 millimeters. The concrete section is ballasted with water, sinking it slowly into the trench under the guidance of remotely operated vehicles and acoustic positioning systems. Divers inspect every joint. Hydraulic jacks push the new section tight against the previously installed one, compressing rubber gaskets to form a watertight seal, tested to withstand 12 bar of hydrostatic pressure. Then the trench is backfilled with rock armor and sand, burying the tunnel section under meters of protective seabed material. This process repeats, section by section.
Right now we are standing 60 meters below the ocean floor. The machine ahead of us is grinding through rock at 300 bar of pressure.
For the first and last 20 kilometers of the route. But between those shallow approaches lies the deep central section of the strait, 80 kilometers of open ocean, where the water is too deep and the currents too violent for immersed tubes. Here, the tunnel must be bored through living rock beneath the seabed. This is where the tunnel boring machines enter. 4 of them, each one a 17-meter diameter earth pressure balance shield, 150 meters long, weighing over 4,000 tons, manufactured by a consortium of Chinese and German heavy engineering firms. 2 machines launch from Pingtan heading east, 2 launch from Hsinchu heading west. They will meet in the middle, somewhere beneath the deepest part of the strait, after years of continuous boring. The TBM is essentially a self-contained underground factory. At its front, a rotating cutter head studded with dozens of tungsten carbide disc cutters grinds into the rock face at pressures exceeding 300 bar. Behind the cutter head, the earth pressure balance chamber maintains a precise balance of excavated muck and slurry pressure against the surrounding groundwater and earth pressure, preventing catastrophic inflows of seawater. One miscalculation in that pressure balance, and the ocean breaks through. Behind the pressure chamber, a segment erector arm, a massive hydraulic manipulator, picks up precast concrete ring segments from a supply train and positions them against the tunnel wall with millimeter precision. Each ring is made of 7 segments plus a keystone wedge, bolted together and sealed with hydrophilic rubber gaskets that swell on contact with water, self-sealing any micro-leaks. The TBM pushes off the newly installed ring to advance forward, and the cycle repeats. On a good day, each machine advances 12 to 15 meters. On a bad day, when it hits a fault zone or an unexpected pocket of pressurized water,
We are standing on a man-made island in the middle of the Taiwan Strait, 65 kilometers from the nearest coastline.
it advances 0. The fault zones are the nightmare. When the TBM approaches a mapped tectonic fracture, the entire boring operation slows to a crawl. Probe drills extend 20 meters ahead of the cutter head, sampling the rock and testing for water pressure. If high-pressure water is detected, chemical grouting is injected through the probe holes, a mixture of polyurethane resin and microcement that penetrates the fractures and hardens into a waterproof plug. The TBM then advances through the grouted zone at 1 or 2 meters per day, its operators monitoring a dozen pressure sensors in real time, watching for any spike that signals a breach. In the worst-case scenario, an emergency bulkhead door behind the TBM can be sealed in under 90 seconds, isolating the flooded section and protecting the crew. Every cross-passage between the twin bores, spaced every 350 meters, is fitted with identical pressure-rated doors. These are not optional features. They are the difference between a manageable incident and a catastrophic loss of the entire tunnel section. At the midpoint of the strait, roughly 65 kilometers from either shore, something rises from the ocean that has no natural right to exist. An artificial island. A steel and concrete platform anchored to the seabed with tension leg moorings and gravity-based caissons sunk into the ocean floor. This structure serves as the tunnel's primary ventilation shaft, emergency evacuation point, and operational monitoring station. Fresh air is forced down into the tunnel through massive axial fans, each one 6 meters in diameter, pushing 300 cubic meters of air per second through dedicated ventilation ducts that run the full length of the tunnel. Exhaust air, heated by train friction and electrical systems, is drawn up through separate shafts. In an emergency, the ventilation system reverses, creating a breathable escape corridor for passengers moving toward the nearest cross passage and up to the surface. The island also houses backup power generators, fire suppression systems, and a helicopter landing pad for emergency medical evacuation. It is built to survive typhoons, rogue waves, and a direct seismic event. Its existence is the single reason a tunnel this long is even theoretically survivable.
17 years of construction, 4 tunnel boring machines buried forever under the ocean, thousands of workers.
Below the island, the 4 TBMs are converging. The 2 eastbound machines from Pingtan and the 2 westbound machines from Hsinchu have been boring toward each other for over 6 years. As they close to within 500 meters, precision becomes everything. Gyroscopic laser guidance systems mounted inside each TBM track its position in 3-dimensional space with an accuracy of 5 millimeters over the full distance traveled. Survey teams on both sides cross-reference measurements using surface GPS, underwater acoustic transponders, and through-the-earth electromagnetic signals. The alignment tolerance for breakthrough is 30 millimeters laterally and 15 millimeters vertically. When the cutter heads of 2 opposing machines finally grind through the last meters of rock separating them, the breakthrough is not dramatic. It is precise. It is measured. And it is the culmination of several million man-hours of labor, 4,000 tons of rotating steel, and an act of navigational accuracy that rivals spacecraft docking. The machines are then disassembled in place, their components too large and too deep to extract, and entombed in specially constructed chambers within the tunnel structure, permanent monuments buried beneath the ocean. Now comes the fit-out phase. The bare concrete bore must be transformed into a functioning high-speed railway. Track slab is laid, a continuously reinforced concrete bed that supports the magnetic levitation guideway, precision ground to a surface tolerance of 0.5 millimeter over any 3-meter span. Catenary power systems are installed overhead if conventional electric traction is used, or embedded guideway coils for maglev propulsion. Signaling and communications cables are threaded through dedicated cable trays running the tunnel's length. Fire suppression systems, high-pressure water mist nozzles spaced every 25 meters, are tested and commissioned. Drainage pumps are installed at the tunnel's lowest points to handle any groundwater seepage, automatically activating if water collection sumps reach trigger levels. Emergency walkways with photoluminescent strip lighting guide the way to the nearest cross passage in total darkness. Every system is redundant. Every component has a backup, because once that tunnel is sealed and operational, the only way out is forward or back.
They said it was impossible, but engineers just build. For more stories of impossible engineering, subscribe.
The first test train enters the tunnel from the Pingtan portal on a Tuesday morning, 17 years after the first survey ship fired its sonar pulse into the strait. It accelerates to 420 kilometers per hour through a tunnel so straight and so precisely bored that the curvature of the Earth had to be accounted for in its alignment. The crossing takes just under 19 minutes. At the far end, the train glides into the underground terminal at Hsinchu, its passengers having traveled 130 kilometers beneath one of the world's most turbulent ocean straits without feeling a single vibration from the water above. What once took hours by air, including check-in, security, boarding, flight, landing, and transfer, now takes less time than a morning commute. Freight capacity between mainland China and Taiwan increases by an estimated 400% in the first year of operation alone. The economic models predict the tunnel pays for itself within 35 years. An optimistic figure, but one that does not account for the geopolitical transformation of making 2 separated economies physically, permanently, irreversibly connected by a concrete tube buried under the ocean floor. The Taiwan Strait Tunnel is not just an engineering project. It is an act of defiance against geography itself. 130 kilometers of pressurized rock, seismic fault lines, and violent ocean currents, defeated not by a single brilliant invention, but by the relentless, grinding, unglamorous accumulation of 10,000 precise decisions made correctly, one after another, for 17 straight years. The ocean does not care about politics, economics, or ambition. It only respects engineering. And somewhere beneath those dark, cold waters, the concrete holds.
130 kilometers of ocean, 3 active fault zones,